Good day. Today we continue the lecture on design for strength, and this we are going for the lecture 10. Now, in our earlier lecture we have discussed about various failure theories for design, and those theories were based on the design for static loading. Now, one thing is there, when we did some example problems, you have seen the condition of the stress at a point was equated with what? It was equated with the material property, mainly yield point stress for ductile material and the ultimate strength point stress for the brittle material. Now, actually in the design we normally do not take into account the full strength of the material. That means, the expression should not have been equated with the full strength like the sigma yield point or sigma ut respectively. What we do is that we consider one factor, what you can see as written over here, the allowable stresses or the factor of safety. Now, this factor of safety one should use in the design, and those factor of safeties are basically based on to the yield strength and ultimate strength of a material. Now, you have by now already know that how a material is being tested, say for a tension test in an universal testing machine. Now, these universal testing machines are used for testing of the materials, and where we get a yield strength of the material, the ultimate strength of the material and the ultimate fracture point. Just to have a very quick recapitulation, just you remember that we had if we consider a tension test, that this is a strain direction and this is a stress direction, which we define as load acted upon by the cross sectional area of the specimen. Now, here we call normally, as you know, that this stress is an engineering stress, okay, because we do not take into account the continuous reduction in area which takes place while a simple tension test is being held. Now, if we plot the sets of data for the strain and corresponding stresses, then we get a curve something like this. Now, in this case, normally this is being called as the yield point, whereas the proportional limit is little ahead, and this is the yield point from where the plastic flow begins, and then we are having an ultimate stress point and we are have a somewhere at a fracture point. Normally the fracture point to be little above, maybe somewhere around here. This is a schematic representation. So, this represents your sigma ut, sigma y, and this is the zone where it is coming out to be the fracture. Now, in some materials like structural steels of mild steel, you might be have seen in the experiment or in the figures in the book that you get situation like this, where you are having an upper yield point and a lower yield point, but this behavior is not common for all materials. Now, in this case, the general trend of this type of stress strain curve, as you know, is something like this. And also you know that just to get this yield point where there is no definite yield point is available, what we do? We draw a line somewhat, well, consider this line to be parallel, somewhat a parallel line to this one to intersect at this point, and this is what we call as an offset. What is this offset? That this is basically something around 0.2 to 0.5% strain of the based on gauge length. Now, this value can be also around 0.01, 0.1, 0.2, 0.5, even it goes up to around 1%. So, depending upon the suitability, people can take this type of offset method to find out this yield point in the cases where you do not have any definite yield point. So, I do not go further on this one, this stress strain diagram for a material testing, because already we know that how it is being done, and I think that you must have carried out such experiments in your earlier courses. Now, what was the idea is that we can find out that yield strength and ultimate strength by such experiments. Now, when we have done this type of experiments, then what we get is that for design purpose an allowable stress is used in place of the ultimate strength or the yield strength. That what I was just talking at the very beginning of the day. That means that earlier we have used always the ultimate strength and the yield strength to be the criteria of the failure when we have been using some failure theories. Now, here we decide an allowable stress. Now, this allowable stress obviously is lower than this ultimate strength or the yield strength in design. Why it is being taken? It takes into account the uncertainties what has been listed over here. Some of the salient points have been listed: the uncertainty in loading, inhomogeneity of materials, that you understand that all materials are not an homogeneous materials, there could be defects in the materials, and the load. The first point, the uncertainty in loading, means we understand that always a constant load what we think is being applied may not be there, and there could be some increase or decrease in the load. Decrease of the load from the design one does not matter, but increase of the load from the design value do matter. Now, various material behaviors, that is the corrosion, plastic flow, creep, we have already taken into account of these ideas, particularly creep we have discussed earlier, because an temperature is a continuous high temperature phenomenon, and the corrosion, as you know, we have already know this idea, the plastic flow which also takes place in the material, that all these things material behaviors can be considered as an uncertainties. Now, residual stress is due to manufacturing process, particularly in these residual stresses, although people do relieve the residual stresses in the machine components by proper metallurgical processes like annealing, tempering, etc., but the still some residual stresses might occur. Fluctuating load situation will be also taking up in details, and for the safety and reliability of the product, this allowable stress is used instead of the ultimate strength and or the yield strength. Now, how we define the allowable stress? This allowable stress, as I have told you just now, that allowable stress is set considerably lower than the ultimate strength or the yield strength. So, we define F as, which designates for the factor of safety, is defined as the ultimate or yield strength divided by the allowable stress. Now, normally in the design, if we are considering a material which are brittle in nature, it is better that people take up the ultimate strength of the material, whereas in structural steels like in mild steels for example, the people take yield strength as one of the criteria for defining the factor of safety. Now, this goes the definition of the factor of safety. So, obviously, allowable stress becomes what? This ultimate strength and the factor of safety. So, what we are basically doing? We are doing that this yield strength or ultimate strength is reduced by a factor of safety. So, that value is actually what we call at the allowable stress. Now, again one thing is that the above ratio must always be greater than unity, that is always understood, that otherwise you will not be getting a reduction in the value of the allowable stresses. Then a question might arise that what should be the values of the factor of safety? It really depends from the design to design. A process where a mechanical process for which you are designing a machine component, if you are very confident of all the forces that might come onto the machine member, that means the number of uncertainties that we have just described in the last slide is within your grip, then you might use a factor of safety a lower value. But in cases where really not a good amount of knowledge is present, then to be a safer design one should take up a factor of safety on a higher side. Suppose a case like welding etc., takes a quite a good amount of factor of safety, whereas a simple structural designs for the static load etc., it takes a design factor of 1.5 or 2 like that. So, really this factor of safety depends upon the type of design you are interested for. Now, once we know this particular factor of safety, then we go to the another idea that is called the stress concentration factor. What is a stress concentration factor? I think by now looking at the figure you might have understood something. Now, the idea is that what we did in all our calculations for the determination of sizes while using the failure theories for the static loading, you must be remembering that the problem what we have chosen in the class were simple circular members, and it was acted upon by a simple load. I mean, it was acted upon by torsional load, axial load, bending load. Loading is not a problem, it could be anything, but only thing within the zone where we have taken the stress calculations, there were no changes in the dimension. It was a straight round bar. It could have been a straight rectangular bar. It could have been something like what I have just told you. Now, This type of stress concentration comes into picture whenever you are having some sort of irregularities as has been prescribed over here. This type of irregularities means you can see that we are having a hole over here. Now, once you are having a hole, then the entire situation changes. That means, you have considered the stress here away from the hole to be uniform. What we mean by uniform? That means, the entire load, well, as because I have taken a segment, you can understand that this load, the looking at this particular stress distribution, this member, this machine member was actually under a tensile load. So, when there are no discontinuities like a hole or notches or any fillets like that, then what you are having? You can have a stress simply P divided by A equals to the nominal stress or the average stress, which is uniform. But whenever you come across a hole like this, as an example what has been shown in this figure, you get a stress distribution like this. You can see near the hole the stresses has gone up to a great extent, and this what we are calling over here as an sigma max. So, the idea of always computing the stress as an uniform in tension or something else in bending, torsion is little dangerous whenever there is some sort of irregularities in the geometry. So, that is what we call as an stress concentration factor. Word you do not consider like now, this is a stress concentration, means as if the stresses are concentrated over this zone. Actually, this situation is something like that. If we draw some stress trajectories, it will be something like going over here, then it changes its path. Okay. Something like this, also similar situation, something like this, which is something synonymous to flow past a cylinder when you have been reading your fluid mechanics courses. You know, this is some sort of a streamline if we compare with a fluid mechanics situation. So, we can see the number of stress lines. If you arrange stress lines going through this section, this width of the section, then obviously the same number of stress line is going past a zone where it is compressed. So, that gives rise to some sort of stress intensities, what has been defined as a sigma x in this situation. So, this situation takes into account in the design by a factor called stress concentration factor. Now, here we give a definition of a theoretical stress concentration factor, Kt or Kts. Well, let me tell you that what does it mean. This theoretical stress concentration factor Kt or Kts, Kt is what? Based on the normal stresses, and Kts is used where you get a shear stresses, a situation say a torsion. So, where you use a Kts. Now, this is used to relate the actual maximum stress at the discontinuity to the nominal stress. So, we define a kT equal to sigma max by sigma 0, and kTs in the similar manner we define as an tau max by tau 0, where sigma 0 and tau 0 are the stresses which we define as a nominal stress. Now, one thing is interesting, that this type of stress concentration factors can be determined by just considering the geometrical aspects of the specimen, and thereby these factors, as it has been called as by the word theoretical stress concentration factor. So, it has got no link with the material property. Material property, that means it is independent of the material used in the design. So, this particular values of the kT or kTs as defined in the for the shear can be obtained geometrically. As for an example, we just show one typical curve. So, you can see that this is a flat bar having a reduction of diameter from capital D to small d. Now, these are actually called the, this curve, small amount of curvature is called the fillet, and this fillet radius is given as r. The arrow mark shows a typical loading condition, and this loading condition is a tensile load. Now, it is not all for this particular situation of the flat bar under tension having these geometrical irregularities at this situation, you can have the value of the kT with respect to r by d ratio, and for a given ratio of d by d you get a series of curves like that, where knowing the r by d ratio you can say for this 0.12 you get a value over here, for a d by d 1.2, and you can get the value of the kT. So, obviously, this curve can be used for aluminum, this curve can be used for cast iron, this curve can be used for mild steel, because it is independent of the material property. Now, in this case I would like to just tell you something about this particular fillet. What is the idea is that whenever you understand a machine member is there without any change of cross section, then what we know that there is no stress concentration factor to be used in the design, because there is no irregularity in the geometry. However, if the irregularity of the geometry is there, as we have just discussed, then what will happen, that you have to consider the situations of stress concentration factor. Now, if I make a design like this acted upon by say any load P tensile. So, if you consider this tensile load, then what will happen? There is a geometrical irregularity, and you will be having a discontinuity in the stress lines, and you have to utilize the stress concentration factor. Now, once I have given this load P over here, one thing reminds me that just I go back to the earlier one. See, I have just shown you a typical figure for a load which is acted upon as a tensile load. So, if instead of this tensile load, had it been a, say, if it would have been a compressive load, I mean bending load suppose, then also we will be getting similar type of curves, not exactly the same curves. That means, what I mean to say, that you can same type of flat bar, once you can use bending moment, you find out different type of K factors, U is a normal load, as because over here a tensile load, you have got this type of situations. If it is in the torsional mode, you will get again a similar type of this stress concentration plots. Of course, in that particular case it would have not been KT, but you will be defining as KTS. Anyway, any standard design book will give you, or design data book will give you such series of the curves from where you can estimate the values of the stress concentration factor depending upon your need. Now, what I was just showing you is that if we had a design like this, then we are having a discontinuity, and that calls for use of a stress concentration factor. Now, one thing you should remember, that such abrupt change of the cross section in the designs should be avoided. Instead, one can think of a situation that is like that, a smooth transition from this one. This is what we call as fillet. Now, I think I need not explain you. The smooth transition means from this higher dimension to the lower dimension, means that the stress lines are not abruptly changing, but it takes a smooth change. So, thereby it reduces a stress concentration factor over here, that you might have seen the earlier results, that larger the fillet radius, then what you are getting, that you are be getting the stress concentration values to be the lower. Now, in this way, if we consider the same specimen what we have shown you to explain the stress concentration factor or the genesis of stress concentration factor, I take up the same situation once again. There is a hole in the machine member. So, you understand that there will be a stress concentration. Now, a clever design could be like this. You put two small holes, one before the large hole, another after this large hole. I need not explain, you understand that there will be no sharp change in the stress line, but there will be a gradual change in the stress lines compared to what we had if there would have been only a big hole. To state further, sometimes you have seen, I just draw one side of the profile, say this is what is a bolt. Okay. So, what we consider that if we just ignore this threaded portion, you have a change in dimension, something like this, of course, without fillet. Now, a better result could be obtained if we consider a bolt which has got all through a nominal diameter having a thread profile onto that one like this. So, these are some examples I am just trying to show you and give the idea of the stress concentration. There are numerous such design methodologies by which one can reduce the stress concentration by a clever design. No matter, we will come across the stress concentration factors in design, because no machine member really exists without any geometrical irregularities in actual practice. So, we go back to this slide, that is the theoretical stress concentration factor is defined by this situation. Now, This one I think I have not mentioned, that this sigma 0 and tau 0 is calculated based on to the net cross section. You understand, net cross section means leaving out the whole, you get this value of the sigma 0. Sometimes people do on based on to the what? Based on to the area where there was no hole, that means based on to the gross area, people also compute sigma 0 and tau 0, that will be much more conservative design, I suppose. Now, the two methods are applicable, but net cross section method is more popular. As I told you, this determination of the stress concentration factor is purely a theoretical one. So, and for that reason people can use the numerical techniques like finite element method, which is a very good powerful tool for finding out the stresses, and several experimental techniques are also available, that is that I have shown you here, photoelasticity, brittle coating method. This is a paint, a paint which is having a brittle characteristics, and that shows the yields whenever it is acted upon, because it cannot, it separates very quickly, you know, the brittle material separates quickly and then the yield takes place, and electrical strain gauge methods. So, these are the certain experimental techniques what we use for determination of the stress concentration factor, and the numerical technique finite element method is also quite popular in this regard. Then comes another phenomena which is noted as notch sensitivity. What is this notch sensitivity? You can see it is written how sensitive a material is due to presence of irregularities in a machine member. Actually, the theoretical stress concentration factor for which we had a discussion right now is not totally applicable to all materials. Means, in other words, what we can say, how much intensity of the theoretical stress concentration has gone inside the material. So, that is called the notch sensitivity. So, that means notch sensitivity somewhat gives you physically that is the material totally sensitive to the notches present or it is insensitive to the notches present. So, thereby again a definition comes into picture where sigma max as usual is written as Kf into sigma 0, as you can see in this equation. I need not define what is sigma max at C 0, but in this particular case the Kf is what? Kf is actually the reduced value of Kt. That is what I was trying to tell you precisely, that Kt was a theoretical stress concentration factor, there was no consideration of the material in use. Now, when we consider the Kf, then we call is the total Kt applicable to this typical material or it is, or what is the situation. So, in this particular case this K notch sensitivity has come into picture. Now, this Kf, the notation Kf what has been given over here is also commonly known as Fatik stress concentration factor. This Fatik stress concentration factor you will be seeing later that we will be widely using for the cases where the materials or the machine components will be acted upon by the variable load. Now, this notch sensitivity is expressed very commonly by a term small q and is defined through this expression Kf equals to q Kt minus 1 and the value of q normally lies between q and 1. So, if you want a independent definition of this Kf, then what we can write down, Kf is something as in ratio is the maximum stress in a notched specimen divided by stress in a notch free specimen. So, this is the definition of the Kf what we have been discussing over here, but anyway, so this is coming out to be the Kf equals to 1 plus q into Kt minus 1. So, what we have been discussing, just come down to this one. So, this equation Kf equals to 1 plus q into Kt minus 1 is the definition through which we define the notch sensitivity q. So, basically the notch sensitivity q is actually anchoring between the Kt and the Kf, and this q obviously is the based on to the specimen material or the machine component material. Now, as for an example, the value of q is very low, around say 0.2 for cast iron, and it could be around 8, 859, 0.8, 0.9 something like that for a standard steel, a grossly if I say. And if that means if you can understand that q equals to 0, it is totally insensitive, and q equals to 1 means the total theoretical stress concentration factor is basically the Kf. So, how you find out the value of Kf? You can compute the value of Kt that you have seen, that Kt can be found out from the theoretical or experimental techniques. Then a series of experimental data through graphs is available to find out the value of the q, which is available in any design data book, and then knowing that one can have an idea of the Fatik stress concentration factor or Kf. So, obviously, you can understand that Kf equals to Kt, if one concentrates on to this idea that Kf equals to Kt, then what we get, that this is a very conservative design, means a safe design. Okay. And once again the expressions for shear are similar. What this means? That the way we have defined Kt and Kf, similarly Kfs or Kts also can be defined, which actually will be required for the design where we consider the shear stresses. Now, we now we talk something about the design for variable load. In earlier lectures, we have taken some specific theories of failure for design of the static load, and now let us consider what are the situations one should consider while designing for the variable load. Now, first of all, while designing for the variable load, one important property or important situation is that material property. under variable load. So, although we have seen the simple tensile tests and we have discussed here in this lecture also about the simple tensile test, in the similar manner one can study the material property under the variable load. Now, what is that? In this particular case, just like an tensile test specimen, people do have the specimen for variable load, and these specimen are subjected to repeated or varying forces of specific magnitude. Now, there will be, as because I have told you the variable load, then the variable means there will be a cyclic pattern, and we see that at number of cycles where the failure takes place is recorded. Now, in this particular situation, we can give an example something like this, that if you are considering suppose this pen is a simple wire and you are utilizing this wire for some binding purpose in a field or somewhere. You do not have any plier to cut. Then how do you cut this material, this wire, which I am taking as an example? Do you pull it to cut it apart? No. What you do? You just give a twist, continuous twist. So, what is happening? That if you are giving a twist like this, then you can understand the fibers below this wire suppose is in the tension, and fibers above this one is under the compression. Next instant you twist in this way, it is a tension in this direction, compression in this direction. So, this what I am just trying to tell you, that this is an cyclic loading, continuously you are giving a twist, and then what is happening, that ultimately you will be getting a failure of this wire. So, that you might have experienced in your actual life. So, that is what is meant by the failures in variable load. So, from that you understand how severe the cyclic loads onto a machine member, whereas you could not put it apart into two pieces by simple tension. You can do that easily, just giving few cyclic loads onto that. So, that is the number of cycles required for failure is recorded, and above two steps are repeated for different force magnitudes. A very common type of situation is that here you can see a typical Fatik test specimen. Now, this particular specimen, what is being done is that you can make an experimental setup. I am just showing you a schematic idea, schematic view of this one. Okay. Now, you understand this specimen is mounted on pairs of bearings, so that by an external motor you can give a rotation, and by some means we apply a load if I say, and so corresponding to load F I we can compute the stress sigma I, and in the experiment what it is being done, that corresponding to this load F I, the number of cycles, as we have just seen earlier slide, that number of rotations required for the failure of the material is recorded. Next, suppose I was 1, next time you take another load, say F 2, corresponding stress will be sigma 2 and failure cycles, stress cycles where the failure takes place is N 2. So, this way, by changing the load onto this machine member or this fatigue test specimen, you can have a set of data generated as the stress cycles and the amount of stress generated. Now, one thing is that the word what is called is a fatigue. I think we have told about this word fatigue so many times. So, it is just like an human behavior. Suppose someone is asked that from ground floor to top floor, say in a 3-storied building, you go up and come down in 2 minutes, say, then the amount of exertion you can imagine. And if I say that the same steps to be climbed and come down in 5 minutes, then obviously the stress requirement is much less. So, that way after continuously working for the entire day, we say it is fatigued. So, that is the same thing, and material just by continuously having and cyclic loading, it gets fatigued. One of the simple practical example you might have come across sometimes or you might have seen is something like this. Suppose you take a simple wire, and this wire you are twisting. Okay? Where you require? You want to cut a wire, you do not have any plier. If you just pull it, will it cut? I think it will never cut. But what you do? You just give some rotations like this. That means, you give a cyclic tension compression, tension compression, okay, in the reverse directions for few cycles, then the wire will break. So, this is what we understand by the fatigue failure of the material under a cyclic loading. Now, this experiment is actually originated by R. Moore, and that is the reason this experiment is very popularly known as Moore's experiment. Now, what you get after such data plotted onto this type of schematic diagram, I have just shown you a schematic diagram. You see the abscissor, sorry, this ordinate has got a fatigue strength and the abscissor is a stress cycles in, as I just explained earlier. Now, you can see the more the load or the fatigue stress onto this material, then lesser the number of cycle it can withstand. So, in this case, what happens that if you lower down the fatigue strength, means the fatigue stress up to a point somewhere here, then you can see that within this zone, if somewhere, even if you are giving an varying load like that and the stress generated onto the machine member is within this zone, then the material can withstand an infinite life. So, in terms of cycles, this is a zone called infinite life. So, obviously, you have to keep the stress within this zone, and the converse is this one is an finite life, there is an overlapping zone in between these two, and these are actually low cycle, that is low cycle fatigue. That means, what I was just telling, that climb the stairs in 5 minutes. High cycle fatigue, climb the stairs in 2 minutes. Okay. So, that way we get an behavior. Now, let us talk about this line. This is a very important stress point, and this is called endurance limit of a material. Now, this endurance limit of the material, what has been given, shown here as an sigma E, is not always a true constant line, I mean true parallel line to this x axis. In fact, this is a typical behavior somewhat resembling a steel material. But if we have some non-ferrous materials or alloys, non-ferrous materials or alloys, we can expect, again schematically I am just trying to show you some behavior like this. I am sorry, it is going to this. Anyway, this is a schematic view, something like this. That means, you can see there is no definite endurance limit presence for that one. Anyway, in those cases what we have to do, that obviously the design in a true sense cannot be for infinite life. Of course, this situation of infinite life is not always true, because only thing it might be taking more, it might be taking that more number of cycles compared to this one. Here what I have shown, it is also not very truly a flat, but anyway for the mild steels and others it is possible that we can design for an infinite life, provided we keep the stress level below the endurance limit. And other situation also have shown, this is typically for some non-ferrous materials and alloys. This type of situation comes into picture. Now, in the design, this endurance limit calculation or determination is a very lengthy procedure. As you can see that we have to take up or wait for the days together to find out at which cycle the specimen break, and that again we have to change the load, you have to take another specimen. That way it is not impossible, people have done it, it is being done, it is a very routine test, but it is a lengthy procedure as I have telling you. So, always a designer wants to obtain a quick estimation of endurance limit without going to such lengthy procedure. It is possible that a plot of results of simple tension test, which is a relatively easier and quick procedure, and rotating beam test, the results obtained from rotating beam test can be related, means can give rise to some correlations between these two strengths. And we will try to explore such situations, that whether or what are the correlations which one can develop if we can have a simple test results and the rotating beam results plotted together and obtain some feasible and practically useful correlation. We continue our lecture in the next day. Thank you. Good day. We continue our lecture on design for strength, and today's lecture is lecture 11. We have been considering in the last class the design for variable loads. Now, you remember that we have been talking about the material property when subjected to varying forces of specific magnitude, and for which we took up a typical specimen as shown here, and this is called the Fatik test specimen, and the results for the Fatik test specimen were plotted in this graph, or the this particular graph, where you can see the entire results being represented in the form of low cycle, high cycle, infinite life. And we considered that this particular situation, this line was basically what we called as an endurance limit. That means, any stress which is occurring beyond this, within this zone, if it is applied onto a machine member, then machine will work for theoretically an infinite life. And at the same time, we have also noted one situation, that in case we consider this type of fatigue strength and stress cycles for an materials of non-ferrous and its alloys, then I think that we plotted a graph like that. Anyway, it is coming too close like, but anyway, that what was main interest was that it do not have any specific endurance limit, and for this type of alloys, and this was a representation for a typical steel material, say mild steel or so. Here also this infinite life cycle, where the endurance limit becomes a flat line, is also not exactly true, but however, we consider such line where which gives you the critical zone, means that beyond this line, if we consider the stresses, then the machine member can withstand an infinite life. However, it is not that always we go for infinite life design. Also, we can have a finite life design, where just by modeling these lines, we can find out the corresponding endurance limit corresponding to some cycles of our interest. Well, if we proceed further,